Okay, welcome to Chapter 9, Linear and Quadratic Inequalities. This is the final chapter in the course. And the first section, we're going to talk about linear inequalities in two variables. And then we're going to move on to, in section 9.2, we're going to move on to quadratic inequalities in one variable. And then in section 9.3, we're going to do quadratic inequalities in two variables. So basically the goals of this section will be to sketch. Okay, will be to sketch a linear inequality. Then we're going to solve some problems. We're also going to go through some techniques like using test points to find the solution. So basically what an inequality is instead of being interested in one or two solutions to an equation or to a problem, we're interested in a range of values. So you're going to see what these look like is the following. Okay, basically here you have your classic linear function. Okay, and typically if we're talking about an equation, the solutions to this function, okay, would be points on the line. Okay, however, in inequalities, we're going to be interested in a region that will satisfy a problem. And actually many problems are like this. So the example I gave on the previous slide is, suppose a chemical engineer wants a reaction to occur within a certain time frame, perhaps to limit the number of pollutants that the reaction gives off. Okay, that might not be a single solution, right? You have a time frame, you have a range of values. So when we graph that, it looks like this. Okay, a solution region. Now these are colored, but what will this look like? Say it was to. The reason this is dotted is because it is using one of these two signs. Okay, a dashed line means you're not going to include the line as part of the solution. So suppose you wanted all the values greater than the boundary, this dotted line. That's what it would look like. I'll make it look nicer than that when we do some examples, but that's what it would look like. Okay. In this case, you'd be using a greater than sign. Okay, y would be greater than the boundary. A solid line, so if I was to make this solid, this means the line is included within the solution. Okay? So, we're going to get into an example. Take a look at the example I did here. And I went through various methods to how to solve it. I'm going to use one particular method in my example, so there's a lot of explanation there. But let's get to our practice problems. Okay, so it says graph 4x plus 2y is less than or equal to 10. Okay, and then you're going to determine if the point 1 and 3 is part of the solution. Okay, so here we go. Part A, 4x plus 2y is less than or equal to 10. So you're going to treat this basically like an equation. Okay, at the start, you're going to have to graph this line. So step one is to graph the boundary. I'm going to call it the boundary because when we move on to section 9.2 and 9.3, it will be a quadratic. So it's not always going to be a line. So I'm not going to say graph the line. And what basically I'm talking about is when we head back, I'm talking about something like this. So not the shaded region, not this region, but this region right here, or this line. So it's very simple. I'm going to rearrange into, I'm going to get it into y equals mx plus b form. Okay. So, which will mean I'm going to move over 4x. Then I'm going to divide everything by 2 to give you the following. Okay? So now we're in business because now we know that the slope is -2 and that the y-intercept is 5. Okay? So let's graph it. So we have 1, 2, 3, 4, 5 is the y-intercept. The slope is -2. So what this means is that you can say it rises, well, it depends what you want to say. I'm going to say it rises -2, so it goes down by 2 and then over 1. You could also say it goes up by 2 and over to the left by 1, okay, if you want more points, like that. Okay, now because we're dealing with this symbol, we're going to use a solid line because it's less than or equal to. So that would look like this. Okay, so there's our boundary. I really could have extended this to be, I'm going to have it span the entire graph. There we go. So from here, since it's less than, okay, I'm actually going to shade this region, all this region right here. But how do I show that to be the case? Okay, you could use a test point, and you're going to choose one point from above or below the boundary and see if it satisfies the inequality. If it does satisfy the inequality, then that's part of the solution region and you'll know which region to shade in. If it doesn't satisfy it, then you're going to shade in the opposite region that you chose the point from. So for instance, I could choose this point right here, 0 and 0, because it's very nice. Okay, for 0 and 0, we're going to have, when we plug it back into this equation up here, we would have 4 times 0 plus 2 times 0. Is it less than 10? Well, we're going to have 0 is less than or equal to 10, which is true. So like I said before, we're going to shade in this entire region underneath the boundary. Okay, and I'll just use straight lines and I'll call this the solution region. And that's it. For part B, very simple. Determine if the point 1 and 3 is part of the solution. You can do this graphically. Graphically, all you have to do is look at the point. I'll plot it right here for you. I'll do it in green. 1 and 3. That's 1, and that is 3. There it is right there. It is on the line, and the line is part of the solution set. So, yes, it is a solution. You also could plug this in to the equation, or to the inequality. You could have 4 times 1 plus 2 times 3. The question is it less than or equal to 10? Well, you're going to get 10. 10 is less than or equal to 10, true. So it is part of the solution. So that's basically it, okay? So when we move on to the next problem, it's a very similar problem, except the equation will be a bit different. So hopefully you've tried it now. Pause the video and give this a shot if you were struggling before. But it's so very, very quickly. Okay, this time there's no A and B, it's just flat out graph this. So let's do it quickly. Let's go over what we did. Okay, let's make sure this is coming together. So don't be too confused when the y-intercept is 0. Okay, that is the y-intercept. It is 0. I showed you this example because you're going to divide by -20, which will flip the inequality here and give you 5 over 20x, which is y is 1 over 4x. Okay, so here your slope is 1 over 4 and y-intercept is equal to 0. So there's your y-intercept. You're rising 1, you're running 4, 2, 3, 4. And we can do that again. Rise 1, run 4, 1, 2, 3, 4. Okay. So you're going to have this. Oh, geez, I struggle at graphing with this program. You're going to have this Lovely line. Okay. Now all you have to do is find the solution region. So this is graphing the boundary. Remember, that's step one. Now you're going to find the solution region. And to find the solution region, you actually can do this. You can do this by looking at this equation. Okay, y is greater than 1 over 4x, which means the solution region has to be above the boundary, right? Because if you just focus on this boundary, that is 1 over 4x, right? That's why 1 over 4x. And I made a slight error. I'm sorry. This line should not be solid. It should be a dotted line. Okay. Or a dashed line. Now, back to the solution region. It's going to be above it. You can use a test point. In this case, you can choose a very simple point. You could choose, let's say, 0 and 1. That's right here. Okay, so you would think it should satisfy this. And going into this, y is greater than or equal to, or greater than 0. It does satisfy it. So your solution region is, like I said, everything above. Okay? And there you have it. So hopefully that makes sense. The next example is you're going to be given the graph, and you're going to have to give me the inequality. Okay, so I outlined it quite well in my example, so hopefully it's made sense. If not, let's take a look at it. Now, since we're dealing with lines, it's pretty easy, because you're given, right from the graph, you're given the y-intercept. So the y-intercept is equal to -2 in this case. You can pick another point on the line. Let's pick this point right here. That's the x-intercept. And you can find the slope, right? On a line, as long as you have 2 points, you should be able to determine the slope, because the slope is constant. So here we go. You rise 2. Rise equals 2. The run is -1, right? Because you're going left, you're going up 2 over 1. Therefore, m is equal to rise over run, 2 over -1, which is equal to -2. And you are pretty much done. Because remember, y equals mx plus b, so the boundary must be equal to y equals -2x minus 2. But this is an equation, right? That's the equation of the boundary. But we want an inequality. So now you have to take a look at the solution region. Is it above or below the boundary? The solution region is above the boundary. Also, a solid line implies we're going to be using this symbol. Okay, y is greater than or equal to -2x minus 2. Now you can choose a test point. You can choose 0 and 0. Okay, that's in the solution region. That should satisfy the inequality that you just made. So the question is 0 greater than -2 times 0 minus 2? Is it greater than or equal to? And what you're going to be left with is 0 is greater than or equal to -2. Correct. So therefore, here is your inequality. Okay? Pretty straightforward. And now let's go on to a application. Okay? I outlined a little application here, show you the solution. And I'm going to do a similar one right here. Here we go. Find all possible combinations of tile and stone that can be used to make a mosaic. Tile costs $2.50 per foot squared. Stone costs $6 per kilogram, and the budget for the mosaic is $150. Now you can use graphing technology to represent your solution, or you can do this by hand and sketch it. This is actually a good question, something that you actually could use quite often, and it's particularly in computer programming. This idea can be used quite often when you need a range of solutions. First of all, we're going to have to allocate or specify what variable will go with tile and what variable will go with stone. So I'm going to let x represent the foot squared of tile, not the cost. That's important. And I'm going to let y represent kilogram of stone. That implies that the inequality that we're after here is 2.5x, because that's the cost per foot squared. So say you have 4 feet squared, times that by 2.5, and then you get your overall cost. Plus, similarly, we have 6y. So for instance, if you had 10 kilograms, you go 6 times 10 would give you $60 for those. And this has to be less than or equal to 150, because your budget is 150, so you can't exceed this. So right here, that can't exceed 150, but it could hit it because that's your budget. So therefore we use less than or equal to. And that's basically the answer. If you wanted to graph this, it will look something like this. We can rearrange this in terms of y. So just like before, you're going to graph it just like before, and you're going to have y is equal to your slope will come out to be -5/12x, and 150 divided by 6 comes out to be 25. Okay, so that means your y-intercept is 25. Your slope is roughly like this. I actually went a little stage ahead. This is the y-intercept. The x-intercept could be quite useful here as well if you want to graph this by hand. And the x-intercept in this case, if you make y 0, okay, up here I'd probably use it in the top equation. You're going to have 6y is equal to 150. Therefore y equals 60. And what did I just do? And sorry about that. For the x-intercept, you have to make y equals 0. And you're going to have to get 2.5x is equal to 150. There we go. Then x equals 60. Makes it very easy to graph, but what I want to show you is that the solution region for this question is only this. And the question is why, and you cannot be out of quadrant 1. So it has to be in quadrant 1 because you can't have a negative tile. Okay, can't have negative tile or stone. Okay, so that is the solution region, that very small. And if you graph this in Desmos, online graphing calculator, it will look something like this. Okay, so if I scroll out quite drastically, you'll be able to see the solution region. So if I scroll in, this is what it will look like, and that's exactly what we have. But Desmos doesn't know the restriction. Okay, I could put a restriction, but it has to be in this region right here. That's the boundary, and then in this region where my mouse is. Okay, so that's basically it. that is basically the answer. So you could restrict that. So you could say 2.5x plus 6y is less than or equal to 150. And that is basically saying you are between, for values of x, you're between 0 is less than or equal to x, less than or equal to 60. Okay, that would be your restriction. Also, y is in this region as well. Okay, so there we have it. So work on the practice problems. Once you feel ready, move on to section 9.2.